Welcome to the public AI Cafe today. Today we have a very long session. It's from 3 to 4:30, which is great. And our guest today, you see them already in the videos, is Xavier Salazar. Hello, Xavier. He is from Focus COE. Then we have Themistocle Grenga. Hello, Themistocle. And then we have Andreas Lintermann. Hello, Andreas. And we have Christoph Schweimer, and he will introduce Hidalgo. Hi, Christoph, great that you're here. And we have Teresa. Teresa is my co-assistant moderator from Grassroots Arts. Hi, Teresa. And me, as you all know, my name is Carmen McWilliams. I'm the director of Grassroots Arts and today your moderator. And the talk of this day is how can HPC technologies help AI? So welcome again. I'm very happy also to welcome you as an audience. It's great to see you coming in the door. Great that you're here today in our cafe. And as always, I have to quickly read the rules. Please take notice that the session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speakers express their personal views and opinions. This is not necessarily the official AI for Media project opinion. And this is also, again, important. This whole cafe is funded and part of the present ICT 48 project, AI for Media. So, and what's the Web Cafe about? It is an online forum to gain insights into the European AI scene. It's good for sharing knowledge and experiences and to meet stakeholders for various areas of AI research and application. So it's really good for networking and it's interactive. So when you see the presentations of the speakers, please send us your questions. We will have a Q&A sessions after the presentation. So there is a menu on the right side. Look at it. There is a way of sending to us questions, and we will be very happy to answer them after the presentations. And now we are coming to the main point, to our speakers. Yeah. So Xavier Salazar, he was the inspirator, kick-off organizer of this cafe. His strategy supported innovation at the Barcelona Supercomputer Center and responsible for organizing sectorial webinars on AI for Focus COE, which is basically the umbrella of all these projects. Right, you're here. And then we have Andreas Lintermann. He's from RAISE. That is this project we see here later about. Lintermann coordinates COE RAISE since 2020 and leads the simulation and data lab, highly scalable fluids and solids engineering at the Jülich Computer Center, Forschungszentrum Jülich, Germany since 2014.
Yeah,
he received his... Say?
Sorry for the long name of the sim lab.
For us Germans, it's normal, but English. He received his diploma degree in computer science and his PhD degree in engineering from RWTH Aachen University, Germany. His group develops multi-physics codes in the field of engineering and combines them with novel AI technologies, making use of modular supercomputing architectures. So, welcome and great you're here. And then we also have Christoph here, Christoph Schweimer. He is from the project Hidalgo. And Christoph Schweimer joined the Know Center as a data scientist in 2019 to work in the Hidalgo project on AI-related tasks, which support the workflow of the use cases. He received his Master of Science in Mathematics from the University of Salzburg in 2017. Also, welcome, Christoph. Great to hear you. And then we have our third speaker, Themistocle Granger, is a group leader and researcher at the Institute for Combustion Technology, ITV, at RWTH Aachen University, Germany since 2018. Previously, he was at the University of Notre Dame, USA, where he received his PhD degree in aerospace and mechanical engineering, and at Princeton University in USA. His work focuses on numerical simulation and modeling of multi-phase turbulent reacting flows. He coordinates ITV activities at COEC. So welcome, Themistocle. You seem all to be in Germany besides me. I'm in the moment not in Germany, and Xavier, but it seems a lot of people in Germany. So, okay, now I will hand over to Xavier. Xavier is our, as I said before, our organizer and main moderator today. So I give you, Xavier, the moderator role now. You can show your presentation and introduce what we are going to do today.
Okay,
Yes.
so thanks a lot for the introduction. So I don't have to introduce myself. Thanks a lot for hosting us and for helping us to organize all this session. And thanks everyone, all the audience, for joining in. And so this is the session on how can HPC technologies help AI. So we are two walls that are adjacent, and let's see what we can do together. Okay, so I'm speaking on behalf of Focus COE, and well, the agenda very fast. I will provide a small introduction. I will give the voice to the Centers of Excellence to show some examples on how they are using AI with the HPC technologies and why they are useful, what challenges exist, and all these presentations will be followed by a panel discussion where we will give the chance to all the audience as well to ask any question, anything that you would like to clarify, like write it on the chat, and well, we'll have 30 minutes for discussing and getting to know more about all the Centers of Excellence and what we are doing. And finally, we will wrap up. So first of all, I was telling that I am speaking here on behalf of Focus COE. So Focus COE stands for the Concerted Action for the European HPC Centers of Excellence. So we are the umbrella European initiative that is aiming to help the Centers of Excellence in HPC, like to promote, to get together, to well, maximize all their output and to help them like to be successful, basically. Okay. What are Centers of Excellence in HPC? So that they are like in each and different sectors and each of different applications, like the initiatives that are promoting the use of HPC technologies in all those sectors. Okay, and they are aiming to provide specialized training, to show the tools and to develop tools and applications that are aiming to promote the use of this HPC infrastructure among those sectors. Okay, and well, you will see some examples later on from the three Centers of Excellence. As in general, and Focus COE as umbrella, so we help in maximizing their output. Okay, so how do we do it? So our main channel is the website. You can find it here from hpccoe.eu. And this is a one-stop shop for finding all the activities, all the codes, all the services, all the news, and all the success stories that are being produced of all the centers of excellence. So here we will have 3 centers of excellence, or 3 examples of the center of excellence, but there are many others that you can also check, and that they could be also interesting for you. Why HPC centers are relevant to AI community? So on the one side, so we have many problems that from traditional HPC approaches, they cannot be solved anymore. And there are some AI techniques that are being used for that. So we are using AI, and AI is becoming more and more relevant for delivering our results. On the other side, as well, from the AI community, we also acknowledge there is a stronger and higher need for computational capability, especially for the AI training, but well, that's an obvious need that we have. So let's see several use cases from 3 centers of excellence of how they are leveraging the AI tools. As in general, so we would like to use this session as well to foster or to try to generate collaboration opportunities. And so one initial one, so we were contacted by these Bonds Apps and Stairway. So they are like providing funding opportunities for HPC providers in AI related projects. Okay, and they can be a good opportunity, or we understand they could be a good opportunity. Like if there's something that you as an audience would like to try out, or that you would like to comment or to check with the centers of excellence, this could be a nice funding opportunity to actually collaborate, foster collaboration. So how to do it? You can find it in their website. There is a process for that. There are several cutoff dates. So the next one in the 31st of March, there will be more. So take a look of it. I guess there will be as well some comment in the chat if people from these projects are also attending. So we'll be also happy to share their input. As the speakers were already introduced, I think it's time to give the voice first to Andreas, then to Themistokle, and then to Christoph. So thanks everyone, and let's start the show.
Yes, I will now give Andreas the moderator role. One moment. Always takes a moment. And so you should now be capable, Andreas.
You see that?
Yes, perfect.
Okay, perfect. So yeah, thank you very much for this opportunity to present today the work of COE RACE. RACE actually stands for Research on AI and Simulation-Based Engineering at Exascale. Quite long title, but yeah, I will explain what it's all about. This presentation is obviously not only coming from me, but I have a lot of contributors, people from Forschungszentrum Jülich in Germany, from TU Delft, from RWTH University, and from the University of Iceland, all collaborators within this project. So let me start with a brief motivation. So basically, a lot of data is nowadays generated in science and especially in engineering and also in industry. And what we're aiming at is processing all this data and try to find out how AI can be used to process all this data. And what we're especially interested in is so-called full loop implementations. And what you see basically here is where we have a simulation that generate a lot of data, which run on high performance computers, produce a lot of data, or we have a lot of experimental data at hand that can be classified as big data, and they can be used as input for novel AI technologies that we would like to develop in RACE that make use of the next generation of supercomputers to do the training on these AI technologies, to generate surrogates and models that then in the end can be plugged in again in the original simulation, or can be used to analyze experimental data. They can be used to predict certain things. They can replace certain physics in the simulation. They can accelerate, especially the simulation process, for example, and then even more and faster data generation can be guaranteed, which then in turn can be used again in optimizing the AI technologies that we're developing. And this iterative process can iterate several times, of course. Okay, what are the major objectives of theory race? Basically, it's all about the development of AI methods that go towards exascale, and we do this along certain use cases. So if you look at the light bulb here on the right side, it's a thing of certain components. On the one hand side, we have an exceptional hardware infrastructure. So we have different HPC centers, European-wide known HPC centers in the consortium with specialized hardware, with large-scale HPC machines that we can make use of. Then, of course, we rely on a certain software infrastructure, and we, of course, do not want to reinvent the wheel. So we basically make use of available software packages like PyTorch, TensorFlow, etc., and make them apply them to different kind of use cases. And we have so-called computer-driven use cases and data-driven use cases, which I will come to in my next slide. And then what it's all about, we would like to develop for these use cases software, of course, yeah, so machine learning models, deep learning models, etc. So we would like to provide to the community the codes that we produce, the data that we produce to get to do the training on, and also, of course, in the end, the fully trained models to the academic industrial community. So what use cases are we talking about? I was saying we have computer-driven use cases and data-driven use cases. The left ones here, the computer-driven use cases, you can imagine those as being those use cases that produce their data with the help of large-scale simulations. And as you can see here, most of them are related somehow to computational fluid dynamics, also meaning large-scale simulations predicting the fluid mechanics of for a certain kind of applications. I will talk in more depth about turbulent flow here in my presentation, but we also have a use case on clean energy, where we're looking at the optimization of wind farm layouts. We're looking at reactive flows, so combustion of hydrogen, especially maybe Temesokolo can talk a little bit more about that, which is this one is tightly connected to the next use case, which is on engine design, where we bring this to application. And we also have a use case on coating when it which is about prediction of wetting hydrodynamics. On the other side, we have data-driven use cases, and they mainly bring their data from or get their data from sensors or experiments. We have a use case from fundamental physics, where CERN is, for example, involved, where a lot of data which is collected from the Large Hadron Collider needs to be processed. We have here it says seismic imaging, but this is tightly related to a remote sensing use case. Yeah, so I will talk about the remote sensing part here in my presentation. And then we have a manufacturing use case, which is deals with the prediction of weaknesses in additive manufacturing. We have a sound engineering use case where we want to help blind people in localizing objects in space. Well, then let me dive into the first use case, so which is on turbulent boundary layer flows. So what you see here on the left side, and I hope the video is playing, you see the simulation of a turbulent flow over an airfoil. And when you look closely, you see some movement at the bottom of the airfoil. Yeah, so where we introduce some actuation. Yeah, so some waves that are happening over there. And you look, if you look closer in the corner of this video, you see basically the drag coefficient, and the red line is basically starts where the actuation starts. So what you basically can see that we are able to reduce the drag by this actuation. And we are very much interested in the dependence of the drag net power on the actuation parameters. So on the wavelength of the actuation, the frequency, and the amplitude. So we have highly resolved simulation data at hand. Yeah, you see down here large eddy simulation data, and the flow is definitely turbulent. So we have a Reynolds number of based on the friction velocity of 360, and we're looking at quasi-incompressible flow. Yeah, so the Mach number is 0.1, and for the simulation we're using a finite volume method. So these simulations actually already run on HPC systems and consume, let's say, a lot of computing power. So the data that we have, you see basically here on the right side. So we take a box which lives basically in the region where we have the actuation. And there we take slices which are parallel to the wall, and they are there lives basically the UVW velocity components of the flow, temporally resolved, of course, and the density. And then basically for the training, we use 85%, and for the testing of our machine learning methods, we use like 15%. So what we actually do for now is we're looking at autoencoders for turbulent boundary layer flows. So on the left side, you see a sketch of a general autoencoder where we basically have the slices as input. We have an encoding part, which consists of 2D convolutions with 2 hidden layers and a batch normalization after each activation layer. Then, of course, we reduce it down to a Latin space. And then we have a decoder part to reconstruct basically, again, the flow field. The details you see basically below. Here we have certain kernel sizes and output feature maps. And for the activation, we have a leaky reload function. For the downscaling in the encoder part, we use a max pool operation. For the upscaling in the decoder part, an interpoloid operation, and then we basically can reconstruct from the Latin space velocity field. On the right side, it's a little bit different. Yeah, so we on the left side, basically, there is no physics really involved. Yeah, so no boundary conditions or anything. So that is something we wanted to introduce here on the right side, as you can see. Basically, the left part is similar to the autoencoder part that you see on the left side, yeah, except that we have the velocity potential as output of this this autoencoder, and then we have certain layers which have fixed non-trainable weights. They basically do a linear operation where on the one hand side we have boundary condition where we do padding to all sides that we can more easily compute the derivatives in the next step. Yeah, then we do a derivative computation at the borders, for example, with forward or backward differences, and in the middle of the field with central differences. And then in the end, we compute the curl. We take the nabla operator basically to end up again at the velocity. And the nabla operator, when we apply it to the velocity potential, we basically apply the divergence-free condition, and which comes with this is the incompressibility condition. And then, of course, we obtain again a velocity field, and then we compute the loss, which we then, of course, need to minimize. So let's have a look at the performance of these autoencoders. So on the left side, you basically see the plain autoencoder. So we took the test data set and had a look at the mean squared error loss on the test data set. And basically what you see here is that the plain autoencoder is doing a better job than the physics constrained autoencoder. Yeah, so the red parts on the right side have a higher loss than the ones on the left side. And you could also have a look at the convergence of the loss here in the center image. Yeah, so here you have plotted the number of epochs over the loss. And basically what you see that the plain autoencoder is doing better. Yeah, so you have a faster convergence than the physics constrained autoencoder. And also to have some qualitative results, you see basically on the right side the snapshot of an original image, an image basically generated by the plain autoencoder, and on the right side by the physics constrained autoencoder. So the question is, why does the physics constrained autoencoder does such a poor job? So this is actually something we're investigating right now. So these are current results, let's say, but we're quite sure that it has to do with the incompressibility constraint that we're applying in the physics constrained autoencoder, as the flow is not everywhere fully incompressible. Yeah, so we're working on further integrating further physical constraints, and we also want to do enlarge the training data sets to have a higher accuracy later on, and see what all this brings. So this is all work in progress, let's say. Coming to HPC, of course, we want to do a training as fast as possible. Yeah, so we do a parallelization using PyTorch GDP, and we did some scaling analysis of the plain autoencoder on the Joules booster system. Yeah, it has a lot of nodes, you can imagine, and each node has 4 NVIDIA 100 GPUs, and then basically we increase the number of nodes for a certain problem size. And what you see basically that we have here, you see that on the left side, basically, a quite good scaling up from 4 to 2000 GPUs that we use for the training. When you have a closer look at the efficiency, that you can see basically that the efficiency is quite high, up to 1000 GPUs, and then you get a drop down, but still to above, let's say, 85% efficiency. What comes along with this is, of course, if you increase the number of GPUs, you always want to fill the GPUs as much as possible, so that all of the time they have something to do, let's say, and that their power is used in the most efficient way. And with this, when you do this, of course, you increase also the total batch size. Yeah, and of course, if you increase the total batch size, you then have less frequent updates of the network parameters, and then of course your accuracy suffers. So this is also the reason why you have an increase in the training error, basically. To avoid this, we are working on hyperparameter optimization, so looking at adaptive learning rate and also at adaptation of the total batch size. And the second use case is on remote sensing, and here it's all about land cover classification and prediction. And as you can see, there are Sentinel satellites that circle around the Earth and take a lot of pictures. And these pictures have multiple channels with different information in, and these are then processed to basically to find a land cover classification. Yeah, so to decide basically what is grass, what is crop, what is forest, etc. So what we want to have is a time series of consistent land cover maps, and basically only by having a single input, as you can see here, of a map at a certain time. So this is basically what you see on the left side. Yeah, this is a map that you have basically with the classifiers, and then you have time series for each year. So each of these are time series for years, and then from the first year we take the left cloudiest image, and for each of the pixels in this image, we do an assignment with the highest probability to a certain class in the map. And after that, we do some clustering to find out where are the borders or the interfaces between the different regions. So what is really crop, forest, soil, what are the interfaces between those? Then we generate a training set, what we call here the annual training set production. So we randomly sample basically individual pixels from those, which then comprise the training set. And then we go over to multi-year training set production, where we have random forests, which we feed basically with this information and let them generate a new classifier, basically. So we take the pixels and decide for the pixels which class they belong to with a higher robustness, as we did before. Then you could already say, okay, we now have for the different years these individual maps, but they do not, well, the methods before, they do not really contain information about the dynamics. Yeah, so you might have pixels which change their class. Yeah, so we also would like to include the dynamics of those. So we do another classification into this crop, forest, soil, etc. And then for the different classes, we do a training of a LSTM, which is then able to predict basically also which can also take care of the dynamics in the changing pixels of a classification, so that we end up then basically at the end with a time series of consistent land cover maps. So this is just an example. On the left side, basically you see a true color image of a satellite image, and on the right side you see a classification map for a specific year. So the question is, how does HPC help AI in the context of these two use cases? So let me get back to the Turbine boundary layer use case again. So when I talked about the scaling, I did not really talk about how we were able to reduce the time. Yeah, so which is plotted here in this plot. You see basically the number of nodes. Each node has four GPUs, like I was saying, over the computational time. And actually, we were able to reduce the training down from 64 minutes using 4 GPUs on one node down to 6 seconds on 512 nodes or 2000 GPUs, which is a speed up factor of 460, and which allows us a much faster training. And the scaling analysis was actually only done on 0.25% of the data. So we use only 21 gigabyte of the data set, but we have 8.3 terabytes of data available. So if you could imagine, if we would be able to put these 8.3 terabytes on one node and do the processing on these 4 GPUs, it would require like 303 hours. Yeah, massive amount of time. But if we do the scaling up to these 2000 GPUs, of course, we also get a specific speed up, and it's estimated to have like 40 minutes for the whole training of on this 8.3 terabytes of data. Then on the right side for the remote sensing use case, basically the training so far only uses roughly 100,000 images, and of course in the future we need to include more data for that, which then necessitates to have HPC systems available for the training, and then the inference actually later needs to be performed on all of 100 million images, and this needs to be done very fast in the future, and this then requires an embarrassingly parallel execution. Yeah, so HPC is a must for this use case. Further HPC advantage for this use case is the system heterogeneity. So when I was talking about the clustering for this use case, you remember this can actually be executed quite fast on CPUs, and the training of the LSTM is actually good to perform on GPUs. So heterogeneous systems are, let's say, a good way to efficiently solve these problems. What are collaboration opportunities? So we offer courses in AI and HPC. We have seminars. They're open for all to attend. You can visit our YouTube channel, and we regularly announce it on our website. We have an educational service platform where you can look for courses that relate to AI and HPC, and sometimes also to different use cases. And of course, you're welcome to approach us if you have any additional collaboration ideas, are interested in one or multiple use cases, or if you're working on use cases, if you have new ideas that we could maybe integrate in our research or have a joint research. We could think about organizing joint workshops or seminars for specific topics. And of course, if you require HPC expertise or need support in accessing HPC system, as I was mentioning earlier, we have HPC centers in the consortium. We're happy to help. And with this, I would like to close my presentation.
Yes, thank you. I switch over right away to Themistokle, right? So I will make you now the moderator, because the question answers, I can remind the audience, you please send it to us, but it comes afterwards, like after all the presentations, we're gonna read them and ask the speakers. So please send us your questions. So we see it, no? We saw it, no? Themistokle?
Yes,
Themistokle, we see. Perfect.
Perfect. So thank you for the introduction. So I'm representing here the Center of Excellence in Combustion, and so the work I'm going to present now, of course, is a joint work that we realize at the ITV, but also in collaboration with the other partner at COEC. Let me remember my director, Professor Fitch, as well my colleague Nista and Schumann. So what is COEC? COEC is a Center of Excellence that recently started in 2020, October 2020. So it's coordinated by the Barcelona Supercomputing Center, but it involved many universities across Europe, inside and outside the EU. And the topic of this Center of Excellence, by the name, you can see that focus on combustion, and is to connect the technology and for energy production as well as fuel with the use in industry. And with that, by the name of the Center of Excellence, we focus on the realization of the software that will allow this to realize this connection. And the final scope is to realize a cleaner and more sustainable power and transportation system. So what we have now is a long path through the decarbonization, and the scope of COEC is to give to the industries and to the researcher the tool to make this path happen. The exascale machine that are going to be used in the next future require the realization of software that are now not available right now, and in the COEC we are going to realize this software and make available to the community. So we focus on three let's say, a branch where the first is the advance on simulation methodology, specifically for turbulent multi-phase reacting flow. Then the second, it's more on computer science, so to enable this software to use this HPC machine, and then develop this new algorithm and realize this transition. So I already illustrated the objective. Let me here just remind that we are really realizing a bridge between the physical phenomena and the computation that needs to be done for the design of the new machine. So our main focus is the realization of a numerical simulation. So if you're not familiar, but the direct numerical simulation, really called DNS, are the most accurate simulation that can be realized, and no model are in them. But before, because of these characteristics, is only possible to realize really in simple geometry and can be used only for academic research. While where design is necessary, then large eddy simulation or Reynolds average simulation are realized, but this kind of simulation do not solve all the scale of the physical phenomena. So it's necessary to apply some models for the phenomena that happen at the smaller scale. So in this kind of simulation, it's possible to simulate and design more complex system, and they are cheaper in a computational cost, but are much less accurate. And for us, the is going to realize model that can improve this accuracy. So where we should look to improve in order to improve this accuracy, and where artificial intelligence can help us. First is the mesh realization, so to realize mesh that are faster and dynamically adaptive. The gradient estimator, as was mentioned by Andreas, that can be realized with a classical numerical methods, but also with a true artificial intelligence. Similarly, with the realization of different methods for the time advancement, but also to realize an inverse problem where we connect directly the results and the input and vice versa. In this way, we can realize also a control system through reduced order modeling and artificial intelligence, or to realize some data-driven model for these results. So in this talk, I'm going to focus on some hybrid technique for the closure module of the turbulence. So classically, let me just show a classical equation that is used for the closure of the turbulence. So all the that is a phenomena that happen at different scale, but in LES, the smallest scale are going to be modeled through this equation that you see here, that is called dynamics Bagoriski, and it works and is well used, largely used in all kind of CFD problem. But what we want to realize, it is our ongoing research, is a data-driven approach based on artificial intelligence. Now, you know, several kind of neural network that can be realized. The NN, they are the simplest. They connect an input and output, or multiple input and output, but they miss the spatial information that is instead a key factor for our problem. So for that, we are going to use the CNN that were realized for image recognition and require a large data set for training, but they are able to connect the data that are spatially close. But the one that we are actually use is the GAN, the generative adversarial network, that differently from the CNN, it's composed by two different CNN, and that are trained simultaneously and actually help to each of the neural network help the other to improve in the realization of super resolved field. So how it's going to work? We have a generator of images that go from a low resolution to a higher resolution, and a discriminator instead that recognize if the generated image is a fake or it's a real image. And as usual, with a loss function that are embedded in the neural network. Now, the question for us is if this GAN that was realized for image, you can see here how the cut image has been improved, is going to work for Turbulent. So if we can move from LES field with a very poor resolution, how is the one on the left, to a DNS-like field as the one on the right. Because, and here is your answer, where in this joint PDF, you can see how the model that I show you at the beginning worked in the evaluation of the subfilter scale stress tensor, and how the TSGAN works. So when the points are aligned along this diagonal line, that means that they are equal to the DNS, are much closer to the DNS results that represent our exact solution. So with a classical model, what we have is, what you get is this I, or we call eggs sometimes. So this I, so a circle in the middle. So the results are close, are not dispersed, but they are not perfect. Instead, with the TSGAN, they are nicely aligned on this diagonal. So they are much more accurate. So first question is now the parallelization of the training, because as Andrea mentioned, we have a lot of data for available for the training. They cannot fit on the memory of one node. So we need to split there on a high number of nodes to evaluate the gradients, then averaging the end, and have this multi-GPU, multi-nodes parallelization. So this helps us to improve the efficiency, and actually the results that you are going to see now on the computational performance has been realized with the help of Mr. Sedona and Cavallaro from the RAISE project, and also on the machine that RAISE provided us. So this collaboration between the two center of excellence. So on the first plot on the top left, you can see how the hold time for a given testing accuracy change, increasing the number of GPU. So on the black line, you see the ideal results that we should get, and instead with the green, orange, and blue line, what we actually get with the different size of data sets. What you can see here, that effectively increasing the number of GPU, we can improve the performance. So reduce the hold time for the to get the desired accuracy, but on the other side, see that increasing the number of boxes available, so the size of the data set, the wall time is going to increase. This because when we are having the global batch size constant, the size of the mini batch size is going to reduce, increasing the number of the GPU, and the optimization process will require a large number of iteration. On the next plot, instead, you see that when we fix the mini batch size and obtain a global batch size that is proportional to the number of GPUs, then the results are going to change. And actually, we see that with a smaller data set, it's not really possible to increase the number of GPU because the data available are not enough, and so the training is going to diverge. Instead, with a larger data set, we can obtain a reduction of the wall time close to the ideal one. But for fluid dynamic problem, differently of what we get from the classical image application, the effect of the box size is going to be determined because it's directly related with the scale or the length scale of the fluid dynamic phenomena that are included in the box size. So we can see here, sorry, from the plot in the bottom that actually a larger box size improve the generalization, and we proved these results on a methane air flame, and are going to give you more detail about it later. So, but let me start with a different case where we have a hydrogen flame. Hydrogen is now, and as you can hear from the news, a hot topic for our research because will be probably the fuel for the future, because it's carbon free, so it will help us in doing this decarbonization path, and can be realized using renewable energy. So will be the carrier of energy between the renewable source and the final user. Here there are two examples of flame. One that we call low Karlovitz number, where the message is basically that there is the heat release from the flame strongly affect the shape of the vortices, strongly affect the fluid dynamics, while a high Karlovitz number, the heat release doesn't affect the fluid dynamics, and you can see that the jet looks like a cold jet. So now, can we use a model a unique model for both of these two different phenomena that actually start from similar conditions, so from hydrogen and air combustion? So the classical method used for that, they give some results that are, let's say, enough accurate, but they cannot reproduce all the phenomena that are in it. What we get with the gun, you can see here, where on the left you have the filtered DNS or LES-like field. In the middle, the results from the gun, and on the right, the DNS, so the true field. And you can see that the results from the gun are quite accurate, are not perfect, but they are really close to what we are expecting from a DNS simulation that is much more expensive. So in this plot that we actually use more to identify the error, you can see on the top the results with the classical modem, and on the bottom the results of the gun from for the subfilter stresses. And as I mentioned before, the results more aligned to the diagonal are better than the results are more accurate, are close to the ground truth. And you can see that comparing all these plots, that the GAN provide better results. So not just visually as we see in the previous slides, but also in a quantitative matter, as we see here, they are much better. It's important also to remark here that for these results, each frame was trained, so the model was trained for its specific frame. So the one on the left, the model was trained at local Lovitz and tested at local Lovitz, while the one on the right was trained and tested at higher Lovitz. What we tried next was to realize a mixed training, so to provide to the model during the training process a mixing of both data. And what we get at the end that the performance of the GAN were still really good. That means that the model itself was able to recognize where which kind of flame was treated at the moment. So that was a good success for us. And moreover, if we go to the detail of how the fluid dynamic phenomena were reconstructed in this particular plot that show how air parcel is deformed. So a fluid parcel is deformed if remains a sphere on the top, if it's elongated along one axis or along the other on the two sides of the bottom of the triangle. And if you compare the graph on the left side that are obtained from the DNS data and the one on the right side that are obtained from the GAN with the mixed training, you can see that they basically perfectly overlap. So really the training, the GAN with the mixed training was really able to reproduce all the physical phenomena that we were looking for. Now let's try to do something more difficult. Let's mix 4 different methane flame. So we train on the one on green that we call R2K1 and test on the other, the lower and higher Reynolds number. So the first, obviously, the check is on the same flame, and we work perfectly as the case before. So now let's try to lower Reynolds number, and the reconstruction was still good. When we go to a higher Reynolds number, or on the left, or an even higher Reynolds number on the right, the prediction was still good. So you can see that the red and green line almost overlap. So the results was that they are perfectly working, but what is important, that what we learned was that we have to keep constant two quantities: the filter size with respect to the Kolmogorov scale and the filter size with respect to the flame thickness. So there needs to be a connection between the filter size and some physical quantity, the Kolmogorov scale for the fluid and the flame thickness for the thermodynamic part. So we need, this model can be general, but can be applied only to simulation with the same ratio that we have here. So it was important to know, and we give us a range of applicability of the model with this training. So we know that for a different flame where for a flame where these values are different, we need to realize a different training. To confirm these results, we went back to another methane flame, this time with a different Karlovitz number, so a different ratio between heat release and fluid dynamics. And the prediction was was still good also for the fluxes of the flux of turbulence on the subfilter scale. So that you can see on the left, and as well with a Reynolds stress, the same quantity that we saw before on the right side. So also in this case, the model worked, but again, we have to keep this ratio between filter size and Kolmogorov scale constant, while the one with the flame can be actually changed. What we did as a last check was to change the fuel. So move from having a train on methane and a testing on hydrogen. But what we realized, if we keep the same filter size, that the prediction was not good. You can see here that the green is higher than the red one, so there is a strong over prediction in the jet. But if we rescale the filter so that we match the parameter that we saw before, then the accuracy of the model become much higher. So we keep in mind that we actually need to really keep the ratio between the filter and the Kolmogorov scale on the same value between training and testing. So this is a quantity that needs to be matched to really use this artificial intelligence model on fluid dynamic simulation. So let me conclude my talk, reminding you some training event that the Center of Excellence for Combustion is organizing. You can see some where Fairfax and Korea already did in the last month, but other are coming. Next week, we can see some of the results that I showed today on the Euro HPC Summit week in Paris. And also next week, there is going to be a spring school organized by the Bulgarian Supercomputing Center, where I'm going to show more results on the artificial intelligence application for combustion. For any future training, you can refer to the websites on the top, where we list all the events that we are going to realize on the next future. And with that, I would like to thank you for your attention.
Thank you very much, Dimitri. Very interesting. And now I switch over to Christoph. He's our last speaker with his last presentation. One moment. I have to give him the moderator role. It's not yet there. So, okay. Now, moderator. Yes. Okay.
Okay, I hope you can see my screen with the presentation.
Yes.
Okay, perfect. And thank you very
just
much.
a comment, we are a bit behind on time, so we should mind that if we want to have this panel discussion in the end, so we should try to be on time, okay, to try to be fast.
Okay. Well, yeah, then thank you very much for the introduction. And just a second, I have to get back to the presentation. Yeah, there you go.
We see it.
My name is, sorry?
We see it. It's perfect. Perfect.
Okay, perfect. Thank you. And I want to thank you very much for the opportunity to present today. My name is Christoph Schweimer. I'm working at the NO Center in Graz in Austria, and I'm going to talk about the DIGO project and two of its use cases. First of all, what I want to talk about in general, the DIGO project, then the migration use case and how artificial intelligence is supporting the use case. Then second use case, social networks use case, and give a short summary in the end. First, the Hidalgo project is a European Union funded project where we are applying HPC and various big data technologies for global systems. The project was actually running from December 2018 until February 2022, so it finished just at the end of last month, and it included 13 partner institutions from 7 different countries all over Europe. In this project, we started with 3 global challenges, which we are also going to call use cases, but added a 4th use case in March of 2020. The idea was there to work on these global challenges, or also called use cases, with the help of big data analytics and artificial intelligence. The first one being the urban air pollution use case, where the idea is to simulate the dispersion of pollutants in rural areas. The second one, which I'm also going to talk about a bit more detail today, the use case of forced migration, which unfortunately we currently see a lot in the media. The third one, the spread of the COVID-19 virus, a use case that we have added to the project in March of 2020. And as a last one, the social networks use case that deals with the spread of messages in social networks. At the beginning of the project, we were thinking, how can artificial intelligence now support the workflows of the workflows? At first, of course, in the model creation phase, for instance, by doing data pre-processing, or also by applying various feature engineering techniques. A second opportunity where artificial intelligence can help is in the model execution phase itself, by applying various model auto reduction techniques to speed up the simulation, and also to help with a data-driven estimation of model parameters. And a third point where artificial intelligence can support the workflows is after the simulation, by visualizing the results and also by verifying the results. Next, I'm going to talk about the migration use case, which is dealing with the simulation of forced migration. And as mentioned just a minute ago, this use case has a high real-life relevancy, especially now with the crisis that we are seeing in the Ukraine, and a lot of people are forced to flee because they cannot live where they used to live anymore. This simulation is being done with agent-based models by one of our Hidalgo partners, the Brunel University in London. And some of the goals of this use case are first and foremost to save lives by supporting the governments and NGOs, such that various kind of resources, let those be medical resources, humanitarian resources, food resources, can be assigned to the right places. For instance, refugee camps, but also villages or cities, just where any kind of resources needed. Other goals include to help with the data collections, and also to investigate what happens if a country all of a sudden decides to close its borders. So what is happening in those cases when a lot of refugees would usually take a certain route, and then all of a sudden this route cannot be taken anymore. For this use case, where can artificial intelligence now support is in the beginning at the model creation phase, because this use case needs as an input a graph structure, which we see here on the right-hand side, where the nodes in this graph structure correspond to physical locations. Those could be cities, villages, or also refugee camps. The edges between those locations correspond to direct routes, and the edge weights between the locations are corresponding to the route distances, which we also see here on the visualization on the right-hand side. And we are going to call this graph structure a location graph. So how can artificial intelligence now support creating these location graphs? These graphs have been created manually in the beginning, which is a very time-consuming and tedious process, since for each location pair, you need to compare you need to have a look if this is a direct connection or if it is an indirect connection, which means it goes very close by or it goes through another location. And artificial intelligence now helps creating these graphs and needs as an input just a list of these locations with their GPS coordinates. And in the first step, we are computing with the open source routing machine the fastest driving route between all the location pairs, which gives us a complete graph. So at this point, every location is connected to every other location. And to remove indirect routes now, we are applying an algorithm that we developed that is based on the triangle inequality and a pruning parameter to give us in the end a location graph of direct driving routes. We have applied our algorithm in several different regions. Here I just want to show two different regions in the federal state of Styria in Austria and also an actual case study in South Sudan. And in the latest column here, you see the F1 score where we are exceeding the value of 0.9 for different values of the pruning parameter beta, which is a good result. We also have the opportunity to visualize these location graphs, which we see here an overlap of the direct connections that we have found manually and the connections that the algorithm has found. And here we see actually the overlap for the region in the federal state of Styria in Austria. So overall, artificial intelligence is supporting the use case by creating these location graphs on which the refugee movements can now be simulated. And for the location graph construction, we have also published a paper in scientific reports under the name A Route Pruning Algorithm for an Automated Geographic Location Graph Construction, which you can read up on if you're interested in some of the details. A second use case where we have applied artificial intelligence is the social networks use case. And in this use case, the idea is to simulate how messages spread in social networks. And this use case also has a high real-life relevancy as millions, if not even billions of people use any kind of social network on a daily basis. Let this be Instagram, Facebook, but also Twitter. And in these networks, people can obviously share their own messages or share their own news. A lot of people use it to read the news and gather information. And one of the issues is also, of course, that fake news are being spread in social networks a lot of times. So our idea was, how can we simulate how messages spread and potentially figure out fake news and how these messages spread. And for this use case, we were focusing on the social network Twitter, where we have crawled 14 Twitter follower subgraphs. The crawling of these graphs is on the one side a very time-consuming process, which can take for smaller graphs up to 2 weeks, and for bigger graphs it can actually take up to more than 2 or 3 months. Also, another obstacle with social network data is obviously that the user data is very sensitive since it contains a lot of personal information, the name of the users, maybe the location, maybe their political affiliation, maybe their religion. So this user has to be treated very carefully, and the networks that we have crawled also cannot be shared. So our idea was now, how can we use these crawled networks, take information out of them and recreate or rather replicate them as closely as possible with respect to some topological features. For instance, the density of the graphs or the average clustering coefficient. So now we try to recreate these graphs, and we developed a method that consists of 4 steps. In the first step, we are fitting distributions to the node degrees. And here we are looking at the reciprocal degree, the in degree, and the out degree separately. In the next step, we are sampling the node degrees from these distributions. And now we are trying to connect the nodes via edges, and we are doing this in a probabilistic manner for the reciprocal edges and the directed edges separately. So at this point, we have actually reached a point where we do have a social network, but some of the features of social networks are not at a real world level. So we are applying an edge rewiring technique that increases the clustering coefficient, which is a very important measure for social network graphs. And the basic idea of the average clustering coefficient is that it gives you how many triangles are in a graph. And with this technique, we are able to increase the clustering coefficient to a real world level. In this table here, I just want to show some of the results that we obtained for 3 of the 4 graphs. The smallest graph with around 500 users and the biggest graph with around 50,000 users. And the first line of each cell represents the crawled graph, and the second line represents the created graph. And what we see here is that the density of the graphs only starts to differ in the 4th decimal place. So we're getting a size that's around the same as in the crawled graph. The largest weakly connected component has also a decent size, and the average clustering coefficient diverges naturally because of the networks and how the real-world networks look. But in the created graphs, we were able to reach a real-world level for this feature. And with these graphs, we can now basically these graphs can now basically be used for information spreading. For instance, here we have created a network with 100 users, and let's say this user here posts a message on Twitter. It gets forwarded to all of the followers of this user. For instance, also this user here. And in the second step, we say, okay, this user is also retweeting this message. So it gets relayed to all of the followers of this user. And in a third step, this user is also retweeting the message. So it gets also relayed to all of the followers of this user. And with our technique, we can now create graphs of different size and structure. Also bigger graphs with 100,000 nodes on which are being used to simulate how information spreads in social networks. We have also written a paper about our approach to generate these graphs, which has been accepted to the ACM Web Conference, which is gonna take place next month under the name Generating Simple Directed Social Network Graphs for Information Spreading. And to give a short summary, we have in this project, since it has finished just last month, we have developed 7 AI components for the use cases. They are used in the model creation phase and are there being used as enabling components to start simulations. They're used as model order reduction techniques to speed up simulations. They're also used to improve the accuracy of simulations by a data-driven hyperparameter optimization, and also, as we have seen, as a tool to analyze the data and also visualize. For more information about the project itself, you can also go to the website hidalgo-project.eu. And with that, I want to say thank you very much for your attention and the opportunity to present today.
Thank you very much, Christoph. This was also very interesting. So now we're coming to the end of all the presentations and our famous question and answer session starts. And also it's 15 minutes to go. I will ask the first question and maybe Teresa has one. We're gonna read to you what the audience is sending. So if you have any questions out there, everybody in the cafe, please send it to us. I will take back now the moderation, also the presentation to my slides, or maybe to Sabia. I think Sabia, no? It's better to you. Yeah?
Yeah, I can get it.
I give it to you. I make you the moderator. I think that's
good.
That's good. One moment. So, but meanwhile, I'm also asking my first question, and whoever feels like answering. So we learned a lot about centers of excellence in these presentations. Now, getting in the role, but my company is a small SME in Germany. The question is geared like this: can like an SME just access the center of excellence and use it for development of own AI services and applications? Is that possible? Maybe Jülich? Yeah, Andreas, I would come to you, right?
Yeah, it's definitely possible, but you have to think about that. If you want to use HPC, you use cycles. You certainly want to use cycles on HPC machines. Yeah, so and they are usually not for free. That's the problem when you're a company, at least. Yeah, I mean, when you're in a research field, you can always go ahead and apply for computing time on different levels, yeah, on a national level or on an international level, and ask for computing time for research. But if you're a company, most of the time you don't want to do research. Maybe you just want to do development of your own stuff or inferencing and things like that that are more commercially related. And then it becomes a more difficult thing, I believe, because then it's more to buying computing time and of course, I can speak only for Jülich, for the Jülich Supercomputing Center. We offer the possibility for SMEs and for industry in general to buy computing time. Yeah, well, it's not our main focus. Yeah, so we prefer basically to do joint research with industry, and that could be funded. Yeah, because when you then propose a research topic and you want to work on that together with the industry, then it's easier to apply for computing time. But if you're only a company and want to buy computing time, then it's then of course the HPC centers are available as well. Yeah. Okay. And when it comes to AI services, then it's more of course we support people, yeah, from SMEs, and now I speak only for RAISE, but certainly this is similar for the other COEs. We all have some kind of business that we would like to establish, yeah, for sustainability reasons. So that's always that was always the case, that the EU in the calls they asked us that there should be a work package on business development, yeah, for sustainability reasons. And a model for that could be that we provide within RAISE services around the methodologies we develop. Yeah, like I was saying earlier, we provide it for free, yeah, open access. But if you want to apply things on HPC or if you want to do transfer learning and you need additional training, etc., then this could be something that we could provide as a service. Yeah, but we're not there yet. Yeah, it's something we're looking at.
Yeah, I'm very close, no? I'm in Cologne, so you just tell me.
So maybe I can complete also the answer.
Yes.
So to make the difference, that one thing is the access to the infrastructure, to the HPC infrastructure, and another thing is the access to the applications that are running on top of the HPC infrastructure. Okay, so each of the centers of excellence, they have codes, they have applications that are using and are being used for solving their problems and their specific things. And to accessing those technologies, they should get in contact with each of the partner that is owning that technology or that application. And then, well, it depends on the application itself, that whether it could be open source, it could be like having some access license. Each center of excellence develop their own strategy, and each partner, each owner of those technologies, they have their own way for accessing them. And so if you are, whether if you are SME or whoever wants to use those technologies, well, you could have it for free, or you could have to pay, or it depends on the conditions of each of the owners of those. So, but I think it's important to understand the difference of just using the infrastructure or using
Yes.
the technologies that are running on top of. And in a way, the added value that is provided by the centers of excellence actually is this access to the applications that are already running and that are already in use for that.
Yes. Okay. Thank you. Thank you very much. And Teresa, you have a question?
Yeah, I have more of a general question. For research like this, what are optional conditions, research conditions? Like, what are the conditions in Europe for this type of research, and what would have to be different, or maybe not different, in order to achieve a leading position in the world?
So I mentioned during my talk that we are collaborating with RACE and also maybe because we are close geographically, but also with Turbulent Center. The last 2 years have been difficult because we traveled much less. Anyway, we try to have interaction with the other center of excellence in Europe at universities that are not also working on the center of excellence. We had several exchange with many university, and we talk about ideas. The pandemic part was, of course, affecting this because a conference done on the web platform is not the same than a conference person where you really met and start to talk and do some brainstorming on that. I have to say that Europe it's working well on that. I hope that more center of excellence will be financed. In terms of machine, I have to say that with the booster that we have in Zurich and the new center of excellence that are also creating in the new HPC, not center of excellence, HPC machine in by Cinec in Italy is going to be on the top of that too. So the Barcelona Supercomputing Center. So we are on the top also around the world. So we don't need to really achieve or reach other country or other group of countries that are above us. We can say that we are on the top.
Yes, thank you. I have 2 questions from the audience. And Stefan, question to Andreas Lintermann. Why were these 2 software tools like PyTorch, TensorFlow chosen? Python as an interpreted language is not known for its high performance. There are frameworks that better leverage the power of HPC.
Yes, that's true. Actually, I mean, these were just examples. Yeah, we're trying out things. Yeah, so we're looking at different frameworks and have a look at their parallelization performance, what kind of implementation on a parallel level they already have, and it's just one of a large set of tools. Yeah, so but it's true. Yeah, Python is not the fastest language, yeah, to use. If you compare to Fortran or C, then it's way slower. But I mean, Python is the language of the AI people, yeah. And it's since we're promoting this a lot together also with the Center of Excellence for Combustion, the usage of Jupyter notebooks, yeah, which is just simply suited for the Python execution with the HPC backend. It just makes things simple, let's say, yeah. So this was a first approach, but we're of course looking at other languages and other implementations. And if it's really time critical, then for sure it's also possible in Python to execute C or Fortran kernels.
Okay, and thank you. I hope Stefan is happy. Here, Federico. Question for all the speakers. Which are the bottlenecks that you had and you resolved, or you still have, in terms of codes and related HPC architecture? In brackets, CPU, GPU, or hybrid, or examples?
Well, I can say that the integration of the artificial intelligence in a fluid dynamic code is a big challenge. We are hardly work on that. The inference time is not negligible, and you can see that the model that we were using before were just simple, like let's quote simple, but computationally cheap equation, so reach the same computational time that this model will be really challenging. The bottleneck is the movement of massive data between CPU and GPU, because we have to, and it's the most costly part, since we have this huge array of data that have to go back and forward at each time step. That is the actual bottleneck. The training for our application is not challenging in computational time, because it needs to be done once. So it can be longer, but it's not. While the a posteriori application, so really use the model inside a CFD code, where we do thousands and thousands of time step, is critical for us, and the inference time and the movement of the data is the bottleneck.
Okay, thank you. So this is the questions from us. Xavier, you want to ask a question?
So I think Andreas wanted to answer as well.
Yeah,
Okay,
maybe when it comes to modularity, yeah, so when we have a heterogeneous system, it's also not easy, let's say, yeah, and we're still working on that in a complex workflow that do different tasks at the same time. Yeah, so for example, if you want to run a simulation and want to do online training, yeah, so that you provide during the simulation already an AI algorithm with training data. Yeah, so then you could imagine that maybe the simulation runs best on CPUs, yeah, and you have maybe another module like the booster, which in Jülich, where you have GPUs, yeah, and you need to ensure, let's say, an efficient data transfer between these different modules. Yeah, so this is also quite challenging, but this is something that we're working on. Yeah, so that first of all, if you have if the data structures are similar, that the data that lives in a CFD simulation can directly be transferred maybe to GPU and directly processed, or if you have need to downsample it or compress it to transfer, etc. These are all options that we're considering. But this is ongoing research, let's say.
Okay, thank you.
Okay, so
Sorry, again, it's only 3 minutes.
only 3 minutes. Okay, so I just wanted to raise one question, like targeting Hidalgo, okay, since we didn't get an answer yet. And I think it's very relevant for the kind of use cases. So it's regarding the data management. So when there is sensitive user data that could make it ethical or legally constrained. So how do you manage it, or how do you deal with it?
Yeah, managing data and make it GDPR aware is definitely a big challenge. As we've seen in one of the use cases, the social networks use case, we are dealing with user data. So one way to deal with this is making the data somehow anonymized by hashing everything that could be of information or of interest for people with maybe some kind of bad intentions, but then you also of course lose a lot of the information. So the method presented, we were able to basically anonymize the user data and get rid of the user data, but still keep a lot of the information from the users. We have also another use case where we are using vehicle data where license plates are sometimes shown. So unhashing them or just getting rid of them is one way to be more GDPR aware and deal with very sensitive data.
Okay, thank you. Yes, I think we could go on for the next hour, but unfortunately, this is a live show, and I see also people, also the audience has to slowly go. We also have to go, but it was very enjoyable, and thank you very much. And if you want to come back as speakers or as audience, please come back. We are always very happy to get new suggestions for new talks. And here from this talk, we will have a recording. This recording will go to the speakers from today. If all the speakers give a short email, we agree, then we publish it online in the AI Cafe YouTube channel. And also it's a go to webinar channel, go to stage channel. So you always can see the recording. And I thank you, everybody. I thank you, Sabia, Andreas, Teresa, and Mistokle, and Christoph. Thank you.
So thanks everyone, and also thank you for all the audience for staying there, and as well anyone wanting to contact us, we will be very happy to follow on and to consider any kind of collaboration opportunity. And well, you can contact us. Okay, so thanks a lot.
Okay, have a nice afternoon.
Thanks for the very good organization.
Bye.
Thank you very much.
Bye.
Thanks.
Thank you.
Bye-bye.
Bye-bye.